All right, in this video, we're going to introduce exponential functions, and we'll look at the properties of exponential functions, and then in the next video, we'll look at some examples of using exponential functions to solve problems. So an exponential function is a function in which each successive output value, it really should be an integer output value, is obtained by multiplying the previous one by some constant number. So one example of an exponential function is called the doubling function, f of x equals 2 to the x power. So for instance, if we have x equals 3, 2 to the third power is 8. With x equals 4, 2 to the fourth power is 16. So going from an x value of 3 to 4 doubles our y value from 8 to 16. So that's why we call it the doubling function. So the graph of that looks like this, blue graph here, and I have a table of values from x equals -3 to 3. So some things to note. Number one, notice the further we go to the left on our graph, the closer our graph gets to the x-axis, or y equals 0. And then as we go to the right on our graph, it starts to really grow in terms of our output values. Our output values are increasing here by a substantial amount. So as we go from 1/8 to 1/4, that's not much of a jump, but later on, going from 4 to 8 and then from 8 to 16, the output values increase rather fast. So as our values of x approach negative infinity, or in other words, as our graph goes to the left, our output values are going to approach 0. So for instance, 2 to some very big negative number is going to approach 0 the larger that negative number is. So for instance, 2 to the -50th, and -50 might not be a very, considered a very big negative number, but there's quite a few decimal places before you get your first non-zero digit. So the further out we go, the closer these outputs get to 0. So as we go to the left, our outputs approach 0. And as we go to the right, something like 2 to a very big positive number approaches infinity. So for instance, we have 2 to the 50th power is this very large number here. 2 to the 51st power is double this amount. So the further to the right we go, the more our output values increase. So as we go to the right, our outputs are approaching infinity. So an exponential function is a function in the form f of x equals b to the x, where b is a fixed real number, such as 2. But really, there's only two conditions on b. Number one, that it's positive, and number two, that it's not equal to 1. And that's called an exponential function of base b. So for instance, f of x equals 2 to the x is an exponential function of base 2. Now, the reason why we can't have b equal 1 is because 1 to any power is just 1. So for instance, 1 to the third power is 1, 1 to the -3rd power is 1. So that's why we can't have it at 1. And we also want to make sure that our base is positive, because if it equals 0, that could cause some issues with raising zeros to certain powers. And if it's negative, if we had something like -3 to the 1/2 power, that would be an imaginary number, and we don't want that. So if we make sure that our base is a positive number that's not equal to 1, we'll have an exponential function of that base. So here we have the graph of our doubling function again, 2 to the x. And here we have a graph of 1/2 to the x power. So we can even have a fraction as our base, as long as it's a positive fraction. So notice this one, as we go to the right, is decreasing in output value, versus this one, the 2 to the x, which is increasing as we go to the right. So for our exponential functions, our domain is all real numbers, which means we can input any number we want for x, any kind of number, real number that we want. And the range, all of our output values are greater than 0. So any number we plug into our function, any real number we plug into our function, our outputs are guaranteed to be positive. The point 0, 1 is on the graph of x, and y equals 0 is a horizontal asymptote. So again, what that means is, as we head to the left on this graph and as we head to the right on this graph, our outputs are getting closer and closer to the x-axis, or y equals 0, which is the equation. F is 1 to 1, so in other words, it has an inverse. It's continuous, so we can draw it without lifting our pencil from the paper, and it's smooth, so no sharp edges or jagged points. For exponential functions where the base is larger than 1, such as 2 to the x, our function is always increasing, which means as we go to the right, we're always going to get larger input or larger output values as we head further to the right if our base is bigger than 1. The limit as x approaches negative infinity is 0, so as we head to the left, our outputs get closer to 0. As we head to the right, limit as x approaches positive infinity, our outputs approach infinity. So we saw that earlier. So the graph, if our base is larger than 1, is going to resemble this graph right here. This is called exponential growth. So the further we head to the right, our outputs are increasing, and it's increasing rather quickly. This is called exponential growth if your base is larger than 1. When the base is between 0 and 1, it is decreasing in value, like we saw with g to the x equals 1/2 to the x power. It is decreasing as we head to the right. For that one, as we head to the left, limit as x approaches negative infinity, our outputs are approaching infinity. So if we look at the graph again of 1/2 to the x power, we'll see as we head to the left, our outputs get larger and larger and larger. As we head to the right, so as the limit as x approaches positive infinity, our outputs are approaching 0. So we have this graph here, which is called exponential decay. So as we head further to the right, our output values get smaller and smaller. So we'll see examples of this with things like radioactive dating. So for instance, carbon dating uses this idea of exponential decay. So we do have some special bases for our exponential functions. The two that we had, or the two that will occur the most, are base 10, so like 10 to the x power. It's called the common base. And an irrational base, e, which is approximately 2.718, but this is just an approximation here. It's called the natural base. Now, where this base comes from is the limit as x approaches infinity of this function. So if we put this function into our calculator and plug in a very large value for x, we'll see that we'll get up, to 3 decimal places, 2.718, but it truly does go on forever without any kind of pattern to it. So it's actually an irrational number. We'll see this with things like, exponential growth, exponential decay, things like that. So it occurs quite frequently in applications of exponential functions, which we'll see later on. So, all right, that about does it for this video. Thanks for watching. I'll see you.